Hello and welcome to another edition of Ontology Talk. I'm Adam Pease, and today I'd like to talk about some issues with the suo-kif language, that's the language that SUMO is written in, and how I go about converting it to a strict first-order logic form. All the things that I'm going to talk about today were previously published as an academic paper, if you're interested in citing this work, in 2014. In the reference listed below, and I'll put that up again at the end of this talk. So what is suo-kif? It's based on the original KIF that was created by a large number of people, but including Professor Mike Genezareth, and it's really a sort of simplified form of that much earlier work. Uses a very simple Lisp-like syntax for those of you that might be familiar with programming in that language. It was popular quite a number of years ago in artificial intelligence work. But apart from that very simple syntax, it only has 7 reserved words in the language, very small language, just the logical operators, and, or, not, implies, equivalence, or if and only if, equality, and then 2 quantifiers, for all and exists. So really, really very simple. It does include in SUMO a number of different terms like domain, domain subclass, range, and range subclass, for example, which specify the types of relations and the return types of functions, respectively. It also has a relationship of instance, so specifying that one thing is a particular individual within a given class, or subclass. One class is a subset or a more restrictive class than its parent. We also have the type of formula. And in particular, suo-kif is unusual in that these are not reserved words in the language. They're actually defined in the logical language. So you get a precise logical definition. They're not in some meta language. So all of these building blocks are built up just from the logical operators. And this gives us a great deal more confidence in the correctness of the language because we can actually test those definitions of these fundamental things as part of testing for contradictions in the overall much larger theory of SUMO. So it's not in a separate meta-language where we have to go through a different set of procedures to test it and maybe even a different theorem prover. So it's all part of this integrated one thing, and I think that's a little bit special. And then it also has some constructs for different kinds of variables, row variables. And I'll explain that in just a moment. And then what is TP? Thousands of problems about theorem proving. This corpus of tests has a language, a standard language associated with it, all created by Professor Jeff Sutcliffe for his yearly CASC competitions. And thanks to his tireless work now over several decades and advocating this work, pretty much all of the modern first-order logic automated theorem proving systems can read and write in the Tptp language, at least write proofs that are in TSTP3, so it's a variation of Tptp for proof outputs. It's a very strict first-order language. It uses quite a different syntax than suo-kif. It uses a prologue-style syntax. I'm not really a big fan of that syntax. I think it's pretty much harder to write in, but it's just syntax, right? So it's the sort of thing that anybody can learn. It's more of a matter of preference. But it is strict in being just first order in a number of ways that I'll explain. And first order in a pretty clear syntactic way as opposed to semantically. So again, I'll explain further. And crucially, it's untyped. So we have to take care of that in a way if we want to use a language that has types like SUMO. So why first-order logic in general? And why not use some other kind of logic? Well, I've talked about this in some earlier videos. FOL is a good compromise. I would like to be able to do everything in a classical higher-order logic and use all sorts of different very expressive constructs, but the science of higher-order logic is not quite as far along as that of first-order logic. So there's some issues in the semantics of constructs that I have to work out in order to be able to to systematize this, to make it operational in a theorem prover. And also, it's just a fact that first-order logic theorem proving is much farther along. There are a lot more first-order provers. They perform really fast. There's a lot more testing that's been done in these yearly competitions. So I've, at this point, for computation, for automated theorem proving, used primarily first-order logic. And if you look back to when I started work on SUMO, even first-order logic wasn't really that fast in the year 2000. A lot of people had at that time, and unfortunately still have, the sense that first-order logic is so expressive that it's really hard to do fast, efficient, practical engineering work in the language. That's just not true anymore. So in the past 20 years, in parts, I think, thanks to my challenging the community a bit with large knowledge bases, because SUMO is quite a bit larger than most of the things that the theorem proving community had worked on prior to it being introduced in the competition. Things have gotten better as a result of that and many other forcing functions. And so I'm betting that higher order logic will get better too. Higher order logic theorem proving will get much better too. So instead of just saying it's outside the bounds of performance of the current state of the art, I'm not going to worry about it. Instead, I've always tried to write down everything I know, regardless of the expressivity required. And so that's worked out really well for first order logic because the technology has caught up to the aspirations of work in knowledge engineering, and I'm betting that's going to happen too in higher order logic. It's just a matter of time. So instead of leaving stuff out, I write everything down. But in terms of practical computation, that does present an issue. I've got to be able to send just the constructs that are provable or that are usable in first order over to those provers. If I send the higher order stuff to them, of course, then you'll just have syntax errors. It won't be able to handle them. So we've got to be able to take care of that in this processing process that I'm going to describe. Why not just use Tptp? Well, again, Tptp was created originally largely to handle very small problems that were very difficult, usually problems in formal mathematics. And a lot of the things that we would want as knowledge engineers that can apply to the challenges of doing theorem proving and knowledge engineering in the large, in the same way that things that work really well if you're creating tiny programs, or people were creating tiny programs 50 years ago, you'd like a lot of extra facilities that make your job easy. And so as programs have gotten larger, our facilities, our languages, our tool sets have changed. And the same is true in knowledge engineering. If you've got a very difficult theorem that you want to prove that only has a dozen axioms, your concerns for your day-to-day work are quite different than if you're working with something like SUMO, which has tens of thousands of axioms. And you just need some different stuff available to make your job practical. So that's why we don't use Tptp, again, apart from my preference for a more, what I would believe is sort of elegant and clear Lisp-like syntax instead of the Prolog syntax. So there's some pre-processing needed, and that's what I'm planning to talk about here and explain. So the processing pipeline is as follows. We do some work with caching that helps speed things up, as well as making the programming of the theories easier. I've already mentioned having to eliminate higher order logic constructs from the stuff that we send to the theorem provers. I've alluded to row variables already. I'm also going to talk about predicate variables, and lastly sort prefixing, because as you recall I mentioned that Tptp is unsorted, and SUMO takes advantage of the same facilities that you'd like to have in most modern programming languages of having things be typed, because you can catch more problems early on that way. So first, caching. This is pretty easy. So there are relations like subclass, that if you know that A is a subclass of B and B is a subclass of C, then you can conclude that A is a subclass of C. You also have the issue with transitivity through instances, right? So if A is an instance of B, that's a particular individual, and B in turn is a subclass of C, then you can also include that A is a subclass of C. So that's a slightly more complicated case for caching. It's not just applying the axiom of transitivity. And of course, this does apply to all transitive relations, and there are quite a number of these in SUMO. So you'd like to be able to just trade space for time as a common engineering solution in computer science, cache all that stuff out, and then you don't have to keep applying the axiom of transitivity, finding it, and prioritizing it, and having your theorem prover know that it's really important. You just don't have to worry about any of that because you've got the answer already pre-computed. And sure, it takes up some space, but space is pretty cheap, and the time challenges of theorem proving are really the dominant ones. I mentioned eliminating higher order logic. What does this look like in practice? Well, here's a higher order logic axiom that uses temporal qualification, qualification, so that something holds during a particular time period. It's true during a particular time period. So this axiom says that if during some time t a person possesses an object and that object has a part, then during that same time the person also possesses the part. So we have a non-logical operator. Right? If we have holds during, if it was just implies or ands, yes, those take formulas. Right? Formulas have truth values, and you can have a conjunction or a disjunction or an implication over those formulas that have truth values. I've got another video that I try to see if I can paste in here that talks about the difference between truth values and terms and so forth, if you're not familiar with those distinctions. But the essential thing is here we look for a formula that's an argument to something and then test if that something, that relationship, is actually a logical operator. If it's not a logical operator, like and or not, etc., but in fact it's a user-created term like holds during, then we know there's a problem. We know we're in higher order logic. The argument is a formula, and you're just not allowed to do that in strict first order logic. So I've got to drop those axioms. There's no way around this. You just can't express them in first order logic. It's a mathematical issue that you can't make some arbitrary magical conversion and turn higher order logic expressions and capture their full semantics in first order logic. Now, one thing we can do that's a bit of a kludge, but works for a restricted case, is taking something like predicate variables. And turning them into first order logic. So it's really powerful to be able to say things about all relations of a given type, such that, as I mentioned earlier, a given relation is transitive, right? If something holds between A and B and the same thing holds between B and C, then that relation also holds between A and C. And that's all this axiom says. But you notice here that rel, this instance of transitive relation, appears in the first position, in the predicate position. You're not allowed to do that in strict first order logic. But you want to have this kind of axiom because it's really tedious to have to restate this axiom for every transitive relation you might create. And there are lots of transitive relations in SUMO. It'd be pretty silly to just keep replicating all of that work. It'd just be redundant, and then you might have typographical errors, and all sorts of things can go wrong. You can eliminate all that if you just have predicate variables and types of relations and then axioms about those types of relations. So it's really useful for large-scale knowledge engineering. Right now, there is a solution that some people have chosen in some logical languages. I mean, you could put the notion of transitive relation into the language itself and say that this axiom applies, but then you've got this other thing that you have to worry about. You have essentially another language. And then you also, if you're building things into the language, like transitive relation, presumably it's much harder to change the language over time. You get people to standardize on a language, now you realize, oh, there's another kind of relation I'd like to add to the language. Well, you're kind of stuck until you put out a new version of that language, where if this is just in the set of axioms that comprise the theory, if I think up another kind of relation that's useful, that saves me a lot of time in knowledge engineering and is true and consistent with the rest of the stuff I've said, I can put that in any time I want to. That's a good thing. So in order to process predicate variables, let me give you a little bit of history here. The first thing that we tried, which does work, right, is to put in a sort of dummy predicate. You have a preprocessor that puts the word holds or any other relation symbol first, and thereby moves the relation into the first argument position. Now you can do this, it works, right? But it's inefficient, and it's inefficient because most modern theorem provers care about the predicate in terms of their search procedure. The predicates really have a lot of information in there that helps a theorem prover be efficient in its search process. This eliminates that because it puts holds as the first predicate everywhere, right? Because you have to do this to every single literal in your entire theory, so it's consistent. And that the predicate then appears as the first argument to this sort of dummy predicate of holds. So it's a really bad thing for efficiency, even though from a logical standpoint, of course, this does work. So what we wound up with was doing a different sort of caching of looking at every relation that fit the conditions of an axiom, like being a transitive relation, and then substitute it in for the variable. Now, this, like other forms of caching, does trade space for time for these very general axioms that say, if I have a transitive relation, then the following is true. I wind up kind of having the processing system create a bunch of instantiations of this axiom for different relations. So part, earlier, subclass, and any of the transitive relations in SUMO have a copy of this axiom. But a key thing is that this is created automatically. I don't have to waste my time as a programmer writing this stuff by hand. It just handles it for me. And if I change this axiom for some reason, or if I add a new axiom about transitive relations, the system just takes care of it all for me. That's very efficient, big time saver. All right. So this works. There is a semantic limitation that I've been at least told about. That is, of course, it only handles all of the transitive relations that I've actually defined. It doesn't handle the case of finding problems potentially with this axiom over the set of future relations that I haven't instantiated, but maybe I've talked about in terms of other axioms. So there's a potential vulnerability there. I haven't found that vulnerability in practice. In practice, this just seems to work very well because I really only care about the things that I've already defined for the most part. I'd be interested in the feedback of any very senior logicians that have some good examples that can tell me what's wrong with this. But it's been 20 years. I haven't found any problems with this. I think it works really well in practice, even though there is a bit of semantic loss in this. So let me talk about row variables as well. And these apply when we have a variable arity predicate. And this might be, again, familiar to people that have some background in Lisp programming. In Lisp, you have this at rest variable that's kind of a don't care or matches all of the arguments that come after it. This is really handy. So, for example, in SUMO, we have the variable arity predicate of partition, a partition of a parent into a set of children. And so here's just two examples. So a chemical process is decomposed into either chemical synthesis or chemical decomposition. Communication is an action that is either a stating, a supposing, a directing, a committing, expressing, or declaring. Now you notice that these two statements have the same relation, partition, but they have different numbers of arguments. This is really handy because you don't know what the decomposition is going to be of any class at any point in the hierarchy. Sometimes classes have 2 subclasses, sometimes they have 6, as here with communication. And so I want to be able to use this relationship, but sometimes be able to match freely, not have to enumerate all those possibilities myself for the different numbers of arguments that it can take. And so here's a useful rule for SUMO that uses row variables. So it's an equivalence. So it says if the first part is true, then the second part is true. And it also says if the second part is true, then the first part is true. So if I have a partition with a number of arguments, then I also have an exhaustive decomposition. So there's nothing else that's below it, is what exhaustive decomposition says. And it's also disjoint, right? I can't be a child of, in turn, of any of more than one of those children. Right? Each one of the children is pairwise disjoint. So if those two condition holds, then I have a partition. If I have a partition, then those two conditions hold. Right? And because both partition, exhaustive decomposition, and disjoint decomposition are variable arity predicates, I can't just list all those predicates. I want to be able to just say, well, however many arguments I have, this relationship is true. And the way I handle it is by, again, kind of caching things out, letting a very simple mechanical process take over the grunt work, the tedium of turning this into its actual implemented form. So I just have essentially a macro that spells out all the possibilities. Do I have 3 arguments? Do I have 4? Do I have 5? And I limit it to 7 because I've just never found the need for more than 7. And it's a very simple syntactic transform, and it puts me back in first order. It gets rid of this row variable. Now, again, I've lost something. If in theory I could have infinitely many arguments, or I could have 100 arguments, well, I've lost that because I'm not enumerating all of those. In practice, again, just haven't found that to be a problem. Doesn't seem to be a problem. I may be missing some semantics, but it's not a case that I actually care about in practical reasoning. Sorts is another issue that's very, very valuable. So, in fact, before I implemented this, I would get occasionally some contradictions in theorem proving because the system could just, find terms that didn't fit with the arguments. You could get an answer that you might paraphrase as, the answer is not my left shoe, right? Because left shoe might have been something that it found somewhere in a theory and then applied in the wrong case, in a case where it was just nonsense. And so not only does this help speed things up, it sort of constrains the search space of possibilities for things that can be substituted for variables, but it also eliminates some potential problems of the sort I just mentioned. So the way in which we define sorts in SUMO is a little different than some other sorted languages that will explicitly state the type of every argument. So the snark theorem prover, in particular, has a nice, efficient way to do this in its native language that's not TPTP. Of defining sorts, but actually this isn't really required. As long as you require all of your relations to have defined types, then you can have an automated process deduce the resulting type of any variables that appear as arguments to those relations, and that's exactly what we do. So if we know that the relationship part and the relationship connected both take objects, or instances of the class object as their arguments, then we can automatically deduce in the axiom below that x, y, and z must be instances of the class object. And so the system can automatically convert the first axiom into this new version where we set what's called a type guard, a precondition that requires x, y, and z be objects. And then we can get down to the actual business of seeing if this rule applies. But we don't ever get to the point of trying to apply it unless we can lock x, y, and z down to the type of object. So this is just helps a lot. It helps catch a lot of problems, a lot of inadvertent things that you might say in this logical language, and it can trap them very simply and very early, and it's not really that hard sort of pre-processing to do. There are a few other things that we need to do. TPTP says you can't use a relation with multiple arities. So back when I was talking about partition, spelling it out, I'd actually need to also create different names for a partition with different number of arguments. So I call them partition 1, partition 2, partition 3, etc. You also can't use relations as an argument in TPTP, so I have to create a instance R or subclass R if I'm talking about the relation rather than just using it. These are, again, relatively easy things to do, and they solve this problem. Right, so that's it. That's how we go about translating some of these interesting and very useful practical features in SUO-KIF into a strict first-order logic syntax in TPTP for use in theorem proving. I wouldn't want to be without these things. If I had to be without them, life as a knowledge engineer would just be a lot more tedious and difficult and potentially error-prone too. So it's just useful stuff. Anyway, I hope this gave you some insight into what we do in SUO-KIF and SUMO, and hope you found it enjoyable. And again, if you wind up using this in an academic citation, an academic publication, the citation is below. Thanks for watching.